the last plenary speaker of this year's colloquium, John Smilie from Cornell. John was graduated in Chicago in 1977, and ever since he has been giving contributions to dynamical systems of an unusual depth, usually playing in a very profound way with the roles of affine and complex structures, or even both. I am particularly fanatical about one of his theorems that he published in 1986 in the Annals of Mathematics on ergodicity of polygonal billiards, together with Kirchhoff and Maser, because that's a theorem that when I learned about it, I just started thinking, how can you improve on this? I met John for the first time, I don't know if you remember, in 1991, and by coincidence at that time, or a little bit earlier, he had started to become interested in the dynamics of higher dimensional complex transformations, more specifically the renome map and its versions in higher dimensions. That's something that he has been pursuing ever since, and that produced a very extremely impressive list of papers, many of them together with Eric Bedford, which is really a major contribution to complex dynamics in higher dimensions. And I believe John will be saying a little bit about that in the complex dynamics session later today. But meanwhile, he kept active in his old love of billiards and planar billiards and other subjects related to Teichmüller theory in dynamics. And today, that's the subject of his presentation, is going to speak on polygonal billiards and dynamical systems with low complexity. John Smilie.
Well, thank you very much for that lovely and flattering introduction. So I'm delighted to be here, delighted to be invited back to IMPA. It's a marvelous place to be, and delighted to be able to speak to you. As Marcelo explained, I started off working in polygonal billiards quite some time ago, and then shifted out of the field, and apparently that's what the field really needed in order to take off, because as soon as I left the field, it just developed in phenomenal ways. So I'm happy to be able to come back and kind of cash in on the popularity of the field, which has really developed since I left the field. So yes, happy to be back. So let me tell you what I want to talk about. So if we think about a billiard table in the plane, and I'm not going to require that it's the standard square billiard table, but I want to require that it has some properties in common with the square billiard table. I want to consider a polygon, and I want the angles to be rational multiples of pi. And then billiards, I want to look at billiard trajectories. So a billiard trajectory is a path in the interior of the polygon which moves with constant velocity until it hits the side, where it bounces, so the angle of incidence is equal to the angle of reflection. Okay, so let's see. So some of the so the recent work in this studying polygonal billiards and the related topics of translation surfaces and quadratic differentials and interval exchange transformations have given a great deal of insight into a lot of delicate properties of these trajectories, and sophisticated properties of these trajectories. But what I want to talk about is I want to talk about some facts about billiards that can actually, very down to earth, in fact, facts that can actually be used to improve your game. Okay, so if you're interested in playing billiards, I want to give you some very concrete, practical information here. So if we are in a serious game of billiards, the typical situation is that you have to call your shot, so that you have to prescribe, say, which pocket you want to sink the ball in and what sequence of sides the ball will hit before it goes into that pocket. So the question arises, well, what are possible legal sequences of sides that can be hit by a trajectory? Okay, so if you're a pool player that hits the ball very hard, this can be a challenging problem because this can be a long sequence of sides. So the most classical situation is the case of the square. Okay, so in the case of the square, and let's see, I want to make a couple of reductions of the problem. But we could label the sides and to consider the sequences of sides hit by a trajectory and ask which sequences are allowed and which sequences are not allowed. Let me observe that in the case of the square, if you have a trajectory that bounces off the sides in this fashion, this is, well, let's see. So first of all, if you keep track, well, it suffices to keep track, well, so if you take such a trajectory here, and where it bounces off, if you flip the trajectory, then what you get is a trajectory that goes out this side, and then we'll apply the reflection to this upper part of the trajectory, and then continues up in this direction. So in fact, if you think of, instead of a billiard, let's see, let's make this look, instead of a billiard moving on the square, if you think of a trajectory moving at constant slope, so that when it moves out this side, it comes in on the other side, and when it moves out the top, it comes in on the bottom at the appropriate point, then the sequence of sides that are hit will be the same as this, will determine the sequence of sides that are hit in this billiard situation. So we can study this case, and let me label pairs of sides here, A and B. And then in this context, the sequence of sides that are hit is usually called the cutting sequence. So if tau is a trajectory, then C of tau might be B, A, B, etc. So this sequence of A's and B's determines the sequences of sides that are hit. So if we can solve this problem, what are the sequence of A's and B's that arise in this context, we can solve the original problem. Okay. Now this is equivalent, of course, studying this problem is equivalent to constant Stokes flow on the torus. It's also equivalent. It's also equivalent to considering a line in the plane and asking whether you hit horizontal or vertical sides. Okay, in this formulation, we can think of the, say the vertical sides that are hit come at regular intervals, and the horizontal sides that are hit come at regular intervals. And the slope of this line determines the ratio between those two periods. So this is understanding the sides, the sequence of A's and B's here is relevant, for example, if you're playing the bongos and you want to be able to play a rhythm where you say hit the right bongo 11 times for every 17 times you hit the left bongo, right? Then the question is, what's the pattern of right versus left? Or in fact, if you're watching a musical group and you want to know what the rhythm is and all you can see is which hand lands, you may want to work backwards, understand a particular sequence of A's and B's, and try to deduce, say, the slope of this line here. So if you're playing 11 versus 17, then you consider a line whose slope is 11/17ths, and you determine the sequence of A's and B's that are hit. Okay, so it's I'm not just planning on improving your billiard game. Okay, let's see. So the first solution to this problem. So the first two published discussions of this problem. One was by Christoffel in 1875, and there's a second by Smith in 1877. Very concrete descriptions of trajectories that can arise. These sequences were also studied in detail by Morse and Hedlund in 1940. Okay, so this is a paper in which Morse and Hedlund are sort of in the process of inventing symbolic dynamics. And they were very taken with these particular sequences, and they named them Sturmian sequences. Okay, because they're related to certain functions considered by Sturm, not because Sturm had anything to do with the particular sequences. Okay, and these Sturmian sequences play a central role in various investigations in symbolic dynamics or dynamics of sequences, particularly work of, for example, Rosy and his school in Marseille have studied these in detail. Well, so these have been studied a great deal, but in terms of polygonal tables, this is the only table which has really been analyzed in this fashion, where you can say in detail what the sequences are that arise. So, so I'm thinking it's time that we analyze a second table. Okay, so say, so I want to describe joint work with Karina Ultragrai, in which we consider a second table, and the table we want to look at is the octagon, so the regular octagon. Okay, and there's a similar analysis here. Allows us to go from a billiard in a regular octagon to a straight line flow. It's a little bit more complicated, but only a little bit more complicated. So let me think of the case of this constant slope flow in the octagon. and ask which sequence is sigma in A, B, C, D to the Z arise as cutting sequences of trajectories. Okay, so I'd like to give you the answer, both in the case of the octagon and in the case of the square. So I'm not going to assume that you're familiar with the case of the square. But let me do the two situations in parallel. In fact, I want to analyze the square. To some extent, the analysis in the case of the square will follow work of Carolyn's series, but I'll also modify it so that it's very parallel to the situation of the octagon. Okay, so I'm going to both describe Sturmian sequences and the sequences that can arise in the octagon. Okay, so let's start with the square. And I want to begin with some elementary observations. Okay, so let's observe that the dihedral group, the group of isometries of the square, acts on trajectories and it acts on and symbol sequences. And it acts in a natural way on both. Okay? So in particular, if we have a trajectory and we flip it vertically, we get a trajectory with the same cutting sequence, right? So, or if we flip it horizontally, we get a trajectory with the same cutting sequence. So, say we may assume that the direction of our trajectory is in the first quadrant by applying the appropriate transformation. And in fact, if we're willing to interchange the two letters, we can reflect over this line and we may assume the trajectory is in this set, let me call it sigma 0. So may assume the trajectory is in the first quadrant. So if we are willing to interchange symbols, may assume direction in sigma 0, collection of vectors with slope less than 1. Okay, in sigma 0, if our trajectory is in sigma 0, then I'm going to observe which transitions are possible. So a trajectory in sigma 0, let's look at one here. Okay, in sigma 0, it will be possible to go from B to A. It'll be possible to go from A to B. It'll be possible to go from B to B, but it will not be possible to go from A to A. Okay, so we can encode that information in a diagram where we use arrows to denote the possible transitions. Okay, and let's call this diagram D0. So this is the diagram corresponding to sigma 0. In sigma 1, if we record the transitions, we rule out going from B to B. Let's call this diagram D1. And note that D1 is obtained from D0 just simply by applying the permutation that interchanges the two symbols. And then definition, a sequence sigma in A, B to the Z is admissible if it is, say, compatible with D0 or D1. Okay? In particular, we see that certain trajectories cannot, certain sequences cannot occur at all. Okay? So if you have two B's, then it's not possible to have two A's someplace else in the sequence. Okay? So if you have two B's someplace, then you never see two A's. So, of course, so we have the following fact. A cutting sequence is admissible. Okay. So if we do the same type of analysis for the octagon, so in the case of the octagon, okay, in the case of the octagon, if we're looking at isometries of the octagon that leave the letters invariant, there are only two now, generated by there's the reflection. So we may, applying that, if necessary, we may assume that the direction is in the upper half plane. Okay. And then if we think about the action of D8 here, D8 has 16 elements. And if we look at a fundamental domain for D8 in the upper half plane, or if we look at a fundamental domain for D8 and call it sigma 0, we see that, right. So if we're willing to interchange symbols, as before, we may assume that our direction lies in sigma 0. Okay. And again, let's record the possible transitions that occur. Okay, so we see that in sigma 0, you can go from A to D, or from D to A. You can go from D to B, or from B to D. And you can go from B to C, or from C to C, or from C to B. So we get, and let's call it again. Let me just call this diagram D0. And then if you're in any other one of these sectors, the transitions correspond to the appropriate diagram D sub j, which is obtained by permuting the letters in the corresponding way. So we have, again, we can say that definition, set sequence sigma and A, B, C, D to the Z is admissible. if it is compatible with D0 through D7. Okay, so this is sort of these are the elementary observations. Okay, so now we need to do something one step more sophisticated here to make the next let's see. Okay, so let's start with a cutting sequence, or let's start with a trajectory in the square. So I'm going to return to the case of the square. Okay, and we have some trajectory tau with some cutting sequence c of tau. And what I want to do is add an additional edge. Okay, so I want to add a diagonal edge that crosses the square C. Call it C. And I can consider my cutting sequence with this, I can consider an augmented cutting sequence with respect to A, B, and C. Okay? So the observation is that the augmented, in order to determine the augmented cutting sequence of tau, I only need to know the cutting sequence of tau, not tau itself. So let's take a look. If the cutting sequence, say, cutting sequence of tau is A, B, B, A, B, 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 of this form, then the augmented cutting sequence of tau, what will happen if I'm going from A to B, I never cross C. If I'm going from B to A, I never cross C. If I'm going from B to B, I always cross C. So the augmented cutting sequence has the form A, B, C, B, A, B, C, B, C, B, A. Okay, so okay, so I've got my initial trajectory here. Now, what I want to do is I want to do an operation to the square. I want to do a cut and paste operation to the square. So now, let me cut it along this auxiliary diagonal C and translate half of it to the other side. So here I have C, here I have A, here I have A, and now I have B. So notice that this operation has not changed the cutting sequence of my trajectory. Because when I glue, I've cut along C, and I've glued along B. But when I glue along B, I'm simply joining an outgoing and an incoming trajectory. Okay, next operation, I want to take this parallelogram, apply a shear, which returns it to the square. Okay, so now I have A, B, C, C, A. So I'm applying a linear transformation to this parallelogram. Well, the linear transformation is changing the direction of my trajectory, but it's taking my trajectory to a trajectory, right? It's changing the direction, it's changing the speed at which I'm traversing the trajectory. But what I get is some new trajectory. If this trajectory is tau, let me call this new trajectory tau prime. So I'm getting a new trajectory here, and the next thing I want to do is take my square and play with the labels. Let me drop the label B, okay, and switch my C's to B's. Okay, so if I do that, I've got an A, a B, and an A, and I have a new trajectory here. A new trajectory with a new cutting sequence, but it's a new cutting sequence that we can determine completely from the old cutting sequence. Okay, so let's just investigate here. So if our original cutting sequence was, as we have over there, A, B, B, A, B, B, A, then what did we do? We inserted C's. So we went to A, B, C. We inserted C's between B's. A, B, C, B, C, B, A. Okay, now the next operation was to drop the B's. So I get A, C, A, C, C, A. And then switch the C's to B's. So I get A, B, A, B, B, A. Okay, so what have we done? We've taken our original trajectory. We're assuming it's in sigma 0, right? So it comes in terms, we have groups of B's. And then what have we done? We've taken each group of B's and we've removed one B from it. So let me make a definition. If sigma equals a bunch of B's, A, B, A, then the derived trajectory, sigma prime, is the result of removing one B from each group. Pardon?
Even the groups with only one B?
Yeah, yeah. Just
In that case, it's not happen that there will be sequence with two A's and two B's?
let's do an example. Okay, it's a good question. Before we do an example, let me just observe. What have we just? We've just shown something abstractly. We've shown that theorem, if sigma sigma equals C of tau is so sigma is a cutting sequence, then sigma prime is a cutting sequence. Right? And you're worried about the question of admissibility here, right? So example, let's look at our sequence, say A, B, B, A, B, 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 A. If this is our sigma, then sigma prime would be, so this is admissible, right? It's admissible because there are no, it has two B's, but it never has two A's. And, okay? So sigma prime would be A, B, A, B, B, A. Still admissible, right? Okay, we haven't, no violation here. If we derive again sigma prime, then what happens? So we're removing one B from each group. We'll follow instructions here. So we get A, B, A. Still admissible, but it's of the other type, right? This had been this is a D0 admissible sequence. This is a D1 admissible sequence. Okay, so we've shown that if sigma is a cutting sequence and sigma prime is a cutting sequence, so a corollary is if sigma is a cutting sequence, then sigma prime is admissible. Right? And let's make a definition. A sequence sigma in a, b to the z is characteristic if sigma is admissible and the result of deriving any number of times is still admissible. Okay, so putting together our theorem with our definition, we see that theorem, a cutting sequence is characteristic. Okay, so let's look at the second example here. So this one looks completely possible that this one is a characteristic sequence. Or if we look at, so this is example 2, if we look at A, B, B, A, B, 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 A, B, 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 A. Okay, if we take this for our sigma, okay, so sigma is admissible, right? Because we can recognize it in diagram 0. Let's look at sigma prime. We get A, B, A, B, B, A, B, 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 A. Again, it's an admissible sequence, right? We can recognize it in diagram D0. Second derivative here, we get, well here, so we know that when we see B's by themselves, we just have to eliminate them, right? That's the rule. Here we get A, B, A, B, B, A. Okay, so this perfectly nice admissible sequence cannot, in fact, be a cutting sequence, and we see that by deriving it twice. Right? So by introducing this notion of characteristic, we see that this idea of our conditions on when a sequence is an allowable cutting sequence are fairly subtle, right? Because they can be violated at any step in this derivation process. Okay. Okay, so are we good for Sturmian sequences? Okay, it's a subtle but a neat characterization. This is okay. Almost. There's actually a counterexample to the complete characterization, which would be this sequence A, B, A. Okay? So that's characteristic, but not a cutting sequence. On the other hand, in some sense, this is the only counterexample. That is, given any characteristic sequence, if in deriving it you never come across this sequence or its opposite, then the original sequence can actually be realized by a trajectory. Okay?
Correspond to a trajectory that
No, it's genuinely an unrealizable trajectory. I mean, from the point of view of sequences, the collection of trajectories is not closed in the space of sequences, right? This is something where any finite word can indeed be realized, but the whole thing can't be realized. Right? Let's see, so to be honest, there are also trajectories which sort of go through the singular point with, say, irrational slope, which, okay. So I wasn't being completely honest, but time is short. Okay, so I'd like to now, let's see, I'd like to summarize this and then look at the octagon case. Okay, so summary. Oh. In sum, what we had a square where we had labeled the sides, and we introduced a second region. Let's call the original square S, and we introduced a parallelogram, which we call S prime. Okay. One useful thing about S prime was that it was tilted, deformed in the direction of sigma 0. So it means that when we code with respect to S prime, we're hitting sides less often. Okay, so it's a more efficient recoding. Okay, the other thing about S prime has a second property, which is that it's equivalent to S by doing a cutting and pasting operation. And then the third property is that it's affinely equivalent to S. Okay, that is, we can shear it to get to S. Okay, so there's two ways of getting from S prime to S: cutting and pasting, where we're not doing where we're preserving or just translating, and the affine transformation. Okay, so what we're going to do. So in the case of the octagon, there's also a region that plays this role. So our original octagon let's call our original octagon O. Then there is a second deformed octagon, which I'll call O prime. Okay? O prime has these same properties. First of all, it's tilted in the direction of sigma 0. It's actually more, it's really like this. Okay, so it's tilted in the direction of sigma 0. It can be cut and pasted and returned to O. And thirdly, it's affinely equivalent to O. Okay, the thing that's different in this situation is that the affine equivalence from O prime to O is an affine involution, not a reflection. So it will be an affine involution in that it will the axes will be the horizontal and the tilted line. The horizontal will be flipped. The horizontal line will be a -1 eigenvector, and the tilted line will be a +1 eigenvector. Okay, so it's hard to draw O and O prime because O prime is indeed very distorted. But as we've seen, so what I want to do is for the sake of drawing a nicer picture, I want to make an affine transformation of this picture. Okay, so what I want to do is shear. I want to do a shear, which is going to take this vertical line and straighten it up. Okay, so this will give me a nicer looking picture. Whatever else it might do, it'll certainly give me a nicer looking picture. So what I want to take my octagon, and I want to shear it so that these lines become vertical. Okay, so what I will get is this picture here. So this is A, B, C, D, A, B, C, D, Okay, when I do this, okay, now I'm, okay, so when I do this to O, when I shear O, O prime will now become just a mirror image of O. So O prime will be, let's see, I'm violating my boundaries here. O prime will be this with A, and let me call the sides B prime, C prime, D prime, A, B prime, C prime, D prime. Okay, and these coordinates, the affine transformation that takes me from O to O prime is just reflection. And to get the cutting and pasting, well I'll do the following. I'll take this triangle, glue them together, and then cut along the other diagonal, cut along the D prime, and put it over here. So, okay. So what's the? Let me now redraw this in a more compact form by I'm just doing cutting and pasting operations. I want to just put these regions together here. So what I get is this: A, D, B, C. Okay? So when I started off with a trajectory whose direction was in sigma 0, when I did my transformation over on this board, I've opened up sigma 0 to make it the first quadrant. So I have some trajectory which is moving inside this region. This is identified with this is identified with that. Trajectory which is moving inside of this region. My original coding is just given by which of these sides I cross. My A, B, C, D coding. Okay, and what I want to understand is what the coding looks like with respect to these A, B prime, C prime, D prime sides. Okay, so so what do they look like? They look, they're simply obtained by changing the diagonal. So I've got D prime, B prime, C prime, A, so where these are the opposite diagonals. Okay, so so the situation is I have my trajectory somehow moving through here, and I know it's coding with respect to these initially labeled sides, and I want to determine its coding with respect to these labeled sides. Okay, so this. So note that since if my trajectory is in the first quadrant, my original labeling is simply telling me which squares I go through. If I should ever enter the D square, I'm going to cross the D edge. If I cross the D edge, I've been in the D square. So I can think of my original coding. So let's say my original coding is A, D, C, A, D, B, C, C, B, D, A, something D, A, B, C, 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 B. So my original coding is just telling me which squares I'm going through. Now what I want to determine is when I go through a given square, I want to determine whether say I go through square B, do I hit B prime or don't I hit B prime? Okay, so that's the issue. Okay, so let me just draw square B. Let me focus on square B. Okay, here I have side B prime. Well, on the left of square B, we have square D. And on the right of square B, we also have square D. Below square B, we have square C. And since the top is glued to the bottom, above square B, we also have square C. Okay, so what I see here is that if I go from D to B to C, then I'm dropping the side labeled B. I'm replacing it with a B prime. If I go from D to B to D, then I'm taking my B and I'm turning it into a B prime. Okay, so I'm maintaining my letter B if I go through this way or if I go through that way, and I'm dropping my letter B if I go diagonally this way or that way. So let me say that so definition, a letter in sigma, so in A, B, C, D to the Z, is sandwiched if it is preceded and followed by the same letter. Okay, so what we see here by looking at B is that we'll keep those B's that are sandwiched and we'll drop those B's that are not sandwiched. So so given sigma, so sigma prime, so the so given sigma, sigma prime is the result of dropping non-sandwiched letters. Okay, and as before, we have the theorem that a cutting sequence cutting sequence is characteristic. Okay, as in the case of the square. Okay, so let me just do an example here. Example, if sigma is equal to C, B, 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 C, C, B, C, C, B, D, A, D, B, C, C, etc. B, D, A, D, B, C, C, B, C, C, B, D, B, C, then sigma prime, I'm keeping this, 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 and I'm keeping this. Sigma prime is D, B, A, B, D. So this is an example. This is compatible with the graph D0, and this one is compatible with the graph D3. Okay, so again, I get an infinite collection of conditions which are necessary for a sequence to be realized as a cutting sequence. In the case of the octagon, there's a little bit more you have to say to get sufficient conditions. So what happens in this case is that next talk. What happens in this case? Say that we have some word which is realized in D3. Well, we have, if we want to invert the operation of derivation, what we observe is what happens is the case that, well, if you're going to take something in D0 and derive it to get something in D3, then the word between D and B is actually determined, and the word between B and A is determined. So we can record that information by giving a decorated graph here. C, C, B, D, D, B, C, 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 B, B. So if we if we define the inverse operation, well, so if we make the appropriate add the appropriate fine print, then this notion actually characterizes characterizes cutting sequences in the class of sequences. Okay. I'm prepared to answer questions if there are any.
So let's thank the speaker before. And now, are there any questions? Paul?
Can you do something similar with a hexagon?
Yes, this analysis that I gave actually works in the same way for any polygon, any regular polygon with an even number of sides. The hexagon is a little bit less dramatic because that actually corresponds to a certain way of decomposing the torus, whereas this corresponds to a way of decomposing a surface of genus 2. So as a proof of concept, we do the octagon first here. And then it also works for polygons with an odd number of sides, but there's a little bit of, some things have to be changed in that. Regular polygons with an odd number of sides, but some things have to be changed in that situation. Yeah.
And if they're not regular?
Well, yes, there are some other polygons that I have not covered here in my analysis. So let me say what is it that makes these regular polygons useful. So what I did here when what we were busy doing here, constructing these regions which were affinely equivalent and cut and paste equivalent, what we're really doing is we're constructing an affine automorphism of the surface obtained from O by making the appropriate identifications. So this type of analysis has a chance of working for any surface, any translation surface with a sufficiently large affine automorphism group. And it was shown by Veach that these regular n-gons do have sort of maximally large affine automorphism groups, and that was our starting point here.
In case we are square, you characterize the sequence by successive derivations.
Yes. Yes, so that's true that the b's have to appear either in or n plus 1 sides. So you get some sequences of n's and n plus 1s. Now, which sequences can occur? Well, now let's think of that as a sequence on 2 letters. Okay, and the possible sequences that occur are exactly those sequences that can again be derived. Okay, so you can get a speedier version of this by saying each time you switch from one type to the other type, that the letters occur in blocks that are n plus 1, but you still have to say which sequences of n and n plus 1 can occur. Yeah.
So what is known about polygons in hyperbolics in the hyperbolic plane?
Yes, well, so interesting, I mean, if you think in general about coding dynamical systems, the sequences that come up here are very special. And I didn't really talk about this, in that they're low complexity. So what we've described here is a certain efficient recoding of the sequence, right? So if you think of this as like a file on your hard disk, and you have a file compression utility, okay, so what is a file? That recodes your file in a more efficient fashion, right? So here we have sequences that can be recoded infinitely many times. That is, you can run your file compression utility as many times as you want, and it gets shorter each time. This is a very special property of sequences. It means, in terms of information, it means these sequences are carrying essentially no information. Now, if we were to go to the hyperbolic case, then we get a situation which is more typical in dynamics, and that the collection of sequences we get, it contains more information. There are a larger number of, so for each finite sequence, if you look at words of length n, in the hyperbolic case, the number of words of length n that you see in a given sequence will grow exponentially. In this case, the number of words of length n that you see in the case of the Sturmian sequences actually grows linearly. It's n plus 1. And in the case of the octagon, it's again linear. It's 3n plus 1. So you get just to summarize, billiards in the hyperbolic situation is a different game.
More questions? Okay, in that case, let's thank John Smilie again.
So let me take a moment to thank the organizers for this extraordinarily nice meeting, and I think they deserve a round of applause.